Okay, so we're going to do a review for a covalent assessment that's coming up. You were given a worksheet to work through with this, so you might want to take that out. And before you begin, you make sure you have a periodic table. Can't do any bonding without a periodic table. If you've been having trouble with your prefixes and naming conventions, we're going through practice, so you might want to do that. Take out your notes. You were given two sheets, one that went over sort of how we do them and recognize the bonds. The diatomic molecules you're responsible to memorize. The second sheet had your rules for naming and your prefixes on it. Also, you may want to go back and pull out the original notes that you had, which sort of talked about what the covalent bonds were, comparison of the models, how to identify single, double, triple bonds, how to do the Lewis dot, and structural formulas. You also may want to pause for a second and make sure that you've marked your group numbers so that you can find your valence electrons for your group A elements very easily. Remember, 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. You may also want to mark your metalloids so that we don't get confused on this. Remember, our metalloids start with boron, and then you go over to the next column and you go down to silicon, and you do silicon and germanium, and you go over to the next column and you do arsenic and antimony, and then go over to the next column and you do tellurium and polonium, and then go over the last group 7 and do astatine. So remember, it forms sort of this staircase from astatine to tellurium to arsenic to silicon to boron, with just one underneath those center 3 rows. So remember, our metalloids do not bond with anything that we're dealing with. It doesn't participate in ionic, it doesn't participate in covalent, so we aren't doing them at all. Okay? All right, if you need to get these materials, go ahead and pause for a moment and go get those materials. All right, so you pause the material, pause the video, you got your materials. In class, I had asked you to go through and complete these sentences. And so if you didn't complete these sentences, pause the video now and complete the sentences, but we're going to go through them together. Okay? Ionic bonds occur between non-metal and metal atoms. And generally we say metal and non-metal atoms because we know in that chemical formula the metal atom is always written first, but metals and nonmetals do ionic bonding. Covalent bonds occur between two nonmetals. A nonmetal atom and a nonmetal atom form a covalent bond. When we have ionic bonding, electrons will transfer between atoms. So they're transferred from the metal atom to the nonmetal atom. Electrons are transferred from the metal atom to the nonmetal atom in ionic bonding. In covalent bonding, the electrons are shared between the two nonmetals. So the electrons here are, you get an electron from one nonmetal, you get an electron from another nonmetal, and they're shared between nonmetals. Okay, great. Now we had some terms that we had to be really careful with. So we're going to review what a charged atom was. Well, our charged atoms were ions. Remember that we determined whether an atom was charged by comparing the number of protons in the nucleus to the number of electrons in the orbitals. And if there's a shortage or excess of electrons when you compare them to the protons, then the atom is electrically charged. If you are having trouble with cations and anions and remembering which is which, please go back and review those in your notes. All right, and then protons are our positively charged particles, and they're found in the nucleus of the atom. Those are the particles, the subatomic particle, that uniquely identifies every element. They are never transferred or shared between elements, and we have to be really careful about that. The only time we've ever discussed anything happening with the protons is when we had nuclear decay. Certain types of nuclear decay could change our element, but that was the whole point. If the number of protons change, physically we have a different element than we started with. So you have to be very careful with this. All right, definition of a molecule, just to review. Our molecule is a neutral compound that forms when atoms share electrons. A molecule is just another name for a covalent compound. Two nonmetals or nonmetals, more than one nonmetal bonding together. Our covalent bond is just that force of attraction between two nonmetal atoms that share electrons. Now, number 5 asks you to circle the electrons that could have belonged only to the hydrogen atom before they bonded with the oxygen atom. So pause the video here and circle those electrons. Okay, so you notice everything's color-coded to make it a little easier. Our hydrogens are blue, so this little blue electron was originally to hydrogen, to that hydrogen, that guy's. And then this little blue electron was originally this hydrogen's electron. Remember, hydrogen has one proton. It'll have one electron normally, and that's the only one it shares. So now notice how each hydrogen now has access to 2 electrons. It's electron that it brought to the covalent bond and one of the oxygen electrons. Here's the one that this guy brought and one that the oxygen is allowing him to have access to. And then the oxygen atom now has access to 8 electrons, making its energy level complete as well. Oxygen brought 6 valence electrons. It's in group 6A. And so if we count, we have 1, 2, 3, 4, 5. It has access to this one, 6. 7, it has access to that one, 8 total electrons. And so its energy level is complete as these atoms share electrons. All right, number 6, highlight the electrons that are being shared in the diagram of the nitrogen molecule. Well, this is a nitrogen atom. 5 valence electrons, group 5A. Here's another nitrogen atom, 5 valence electrons in its outer shell. And if we put those together, we get a nitrogen molecule. That's this guy over here. And so it asks you to circle the electrons that are not being shared and highlight the electrons that are. So pause the video here and try that. So I'm going to do this in different colors, but our first pair that's shared are these guys here. The second pair that's shared are those guys there. And the third pair that's shared is that last guy there. So those are our 3 shared pairs of electrons. And it says circle the ones that are not shared. Well, this guy is not shared, and this guy is not shared. I'll change colors as I change to the other atom. This guy is not shared, and that guy is not shared. Okay? So now remember that we didn't circle all 6 and we didn't circle them vertically. We've always practiced pairing things kind of horizontally, so it helps us get to our structural model. So let's take a look at our structural model. Remember, for each pair of shared electrons, you get a single line. So for the top pair, there's my line. Sorry, it's a little crooked. For the middle pair, there's my line. For the bottom pair, there's my line. So I have 3 pairs of shared electrons. That makes a triple covalent bond. Notice the nitrogen molecule has 1 triple covalent bond, 3 shared pairs, a total of 6 electrons shared between the 2 nitrogen atoms. You have to please be able to go back and forth to make that connection. And remember that this is not 3 single bonds. This is single covalent bonds. This is 1 triple covalent bond. If we go back and look at hydrogen and we draw the structural model for for water, my apologies, we ended up with this as the structural model for hydrogen, if you remember. And so this has 1, 2 single covalent bonds. There's 1 shared pair between this guy and 1 shared pair here. And so this is a single covalent, this is a single covalent. So you have 2 single covalent bonds in a water molecule and 1 triple covalent bond in a nitrogen molecule. Remember, there are several diatomic molecules you need to have memorized, and it's a good idea that you can figure out what kind of bond they have as well. All right, definition of nonpolar. This should be a review. Covalent bond in which the electrons are shared equally by both atoms. So the question is, are electrons always shared equally during covalent bonding? And if you need to, pause and look it up, but we should be somewhat familiar with the fact that no, they are not. Sometimes one atom will have a stronger attraction, we've called that electronegativity, to the electrons, and so the shared electrons spend more time orbiting around that atom than they do to anything else, and it causes a slight charge. Now, overall, the molecule is neutral. Recall that to be charged, I have to have an excess or shortage as I compare of electrons as compared to the number of protons. And that's not the case. They have the same number of electrons and protons. It's just where they're sort of spending their time. You could see in this, as we put those two hydrogens in, that the electrons spend a little more time here, and that guy didn't have any electrons around it. So it looks to the rest of the world as though it's just a little proton sitting there, so it's a little bit positive. And this guy has a little bit of an is negative because it has those electrons all orbiting it, and so it then looks like it has more electrons than protons for a little bit. Okay, so pause here if you need to, but it says draw an arrow showing the pull of electrons towards the chlorine atom. And so if we're pulling electrons towards the chlorine atom, we're pulling them this way, okay? And again, this will create a polar bond, a covalent bond in which the electrons are unequally shared. And so it says, why does the chlorine atom have a partial negative charge in the hydrogen chloride molecule up here? Well, if we look at it, hydrogen has one proton. And if its electrons are sort of over here with chlorine, then this end looks like it's a little bit positive because all the rest of the world sees is the proton. And if this electron's spending more time orbiting around chlorine, well, chlorine had 7 electrons in its outer orbital. Originally, it had enough electrons to be neutral with its protons, but now I have 8 electrons orbiting, so I look like I'm a little bit negative. Okay? So again, because that chlorine atom is so large, it has a larger electronegativity. We've done it by molecule at atomic size just to kind of help you visually. Then it has a stronger attraction to those electrons. They just spend more time orbiting around the chlorine. Okay, they're unequally shared. All right. So you're asked to go back and highlight the parts of the water molecule that have a slight positive charge and circle the part that has a slight negative charge. If you haven't done this, please pause the video and go ahead and do that. So if we circle the slight positive, oxygen's the big guy. It had a lot of electrons, so this one was the one that gets more time with those shared electrons. So this is, did I do that right? Yeah, slight negative said circle the slight negative, so that's it. And then highlight the slight positive. Well, that's those little teeny hydrogen molecules down here. They're the ones that have the slight positive charge. There we go. Because they don't spend a lot of time with those electrons, those orbiting them, so they look a little bit positive with that proton's open. Now, this is just a question to think about. Sugar and salt, sort of clear-ish crystals, they look a lot alike, and so the question is why they have a different effect on their food and your taste. So think about what you know about solutions and bonding. Pause the video here and see if you can come up with an answer. All right, so sugar and salt have very different chemical makeups. Salt is an ionic compound, a metal, sodium, and a nonmetal, chlorine, bound together. And so they have a nice structured, remember the lattice structure that's nice and strong for the crystalline. And then Sugar, on the other hand, is a covalent compound. It's carbon, oxygen, and hydrogen to form its molecule, and so they dissolve differently. They taste differently, they dissolve differently, they break apart differently. And so that's what causes this. Okay. So it says, describe the strength of the forces between covalent molecules. Well, compared to ionic compounds, the covalent bonds are not really as strong. Ionic bonds are much stronger than covalent bonds. Okay. This was something that was pulled from an old reading, just an interesting thing to kind of look at the difference between the melting points of some of the different elements. And it says, highlight the information in the table that shows that sugar melts at a lower temperature than salt. And you can ignore this because when I pulled this, I pulled the wrong thing. Sugar melts at 365 degrees Fahrenheit. Salt melts someplace way up here. But you can tell too that this is a solid crystal, right? And then these are all kinds of, I don't know, different substances that are more fat-based. And so if you go back to that whole polar, nonpolar reading on solutions, you can kind of get an idea about the difference in hydrocarbons versus the molecular structure that we were talking about. Our properties of our covalent compound, this comes from an older reading. So for this year, 2016, we are not testing over these things, except for you should know that ionic compounds are excellent conductors. Covalent compounds are not. They don't form ions. This is left over from the solutions unit that you do have information on. So covalent compounds, the electrons share. They have lower melting and boiling points. They're poor electrical conductors. They are generally solid. They could be solid, liquid, or gas at room temperature. Strong bonds between individual atoms, but weak forces of attraction between molecules. They dissolve easily. That's one of the things. Okay, so properties of ionic compounds. Electrons transfer. They have higher melting points and boiling points. They are excellent electrical conductors because they form ions when you put them into solutions. Solids at room temperature. Remember that crystal lattice structure. They have strong attractions between the positive and negative ions because you get the electron configuration stable, but now they're charged, the atoms are charged, and so you're pulling onto that electrostatic force that we studied last semester. And if you remember, the electrostatic force was really strong. All right, so I'm going to pause here and do a separate video for the answer keys to the worksheets. So go ahead and do these if you haven't, and then tune back to the next one.